Hi, my name is Abhinav Agarwal. I am a member of technical staff at Forza Silicon. Forza is a part of Vision Research Business Unit of Amatec. And today it's my pleasure to present at the 60th anniversary of DAC. Today I will talk about how Siemens EDA tools enable us in optimizing our analog, mixed signal design, simulation, and verification flows, particularly in the context of high resolution, high frame rate image sensors. This is the outline of my talk. First, I'll talk about some industry trends and design challenges related to image sensors. I'll give a brief overview about our company Amatec. I'll talk about CMOS image sensors specifically for cinematography applications. Then I'll talk about some challenges in doing verification of image sensors. And then I'll present a methodology and tool flow from Siemens EDA that we use at Amatec to address these verification challenges along with some of the EMIR challenges. Finally, I'll conclude and present a summary. CMOS imaging market has shown significant growth over the last decade. The graph on the left, we can see a CAGR, which is cumulative aggregate growth rate of double digit up until 2024. You can see that there is a dip at 2020 due to the impact of the pandemic. The growth is coming from diverse markets. The graph on the right shows that the smartphone cameras continues to be the largest market. However, with the focus on self-driving cars, the automotive market is experiencing the fastest growth. Internet of Things, industrial and security applications are also having a steady growth. Let's have a quick look of CMOS image sensors and its key components. On the left, we can see a representative architecture of a CMOS image sensor, which has a pixel array, column parallel ADCs, PLL, ISP, DRAM, and a SerDes interface. In the center, we can see a pixel array consisting of rows and columns. If the row is enabled, a signal is sent to a noise cancelling circuit, which is then fed to an analog to digital converter. We also see an example of this in the signal path and an example of global shutter pixel path. So what are the major design challenges in CMOS image sensors? There is always a drive for lower cost while improving the quality and reliability of CMOS image sensors. I would say optimizing noise is the biggest challenge for designers today. They must account for every diverse noise, including thermal, short, KTC, 1/f noise, dark fixed pattern noise and quantization noise. Because of the repetitive structure and signal coupling from adjacent readout columns, switching simultaneously, there is a concern for crosstalk, especially when pixel pitch is close to 1 micron. There are also many switching circuits, multi-modes of operations, and requirements to have higher I/O performance. As these requirements are starting to grow, there is more and more digital integration coming into the picture to mitigate these challenges. Now I will give a quick overview of Forza Silicon and our parent company Amatec. Forza Silicon was founded in 2001 in Pasadena, California. We currently have 42 employees, mostly engineers, having expertise in analog and mixed signal IC design, test hardware design. Over the last 2 decades, we have worked with over 25 foundry processes, mostly dedicated to CMOS image sensor. So far, we have successfully completed over 300 mixed signal designs for several customers in the last 18 years since inception. Over the years, we have also developed more than 80 patents related to CMOS image sensors. In 2018, we got acquired by Amatec, a leading global manufacturer of high technology products for a diverse set of niche markets. Amatec has more than 15,000 employees with support locations in 30 countries around the world with an annual sales of more than $4 billion. Now let's look at Forza Silicon's business model. Significant portion of our revenue comes from providing custom IC design services for CMOS image sensors to cater a diverse set of needs for our customers. We work very closely with our customers to define sensor specification, select the process node, system architecture best suited to achieve the desired performance at the lowest price per sensor. This process involves analog mixed signal circuit design, layout, post-layout extracted simulations, top chip functional verification, and finally tape out to foundry. To expand our revenue stream and provide a complete end-to-end customer solution, we also provide integrated production services, which involves prototype development, wafer probing, qualification, yield optimization, and production part delivery to our customers. Forza has several competitive advantages, making it one of the leading CMOS image sensor design houses in the world. Forza designers have been involved with many of industry's first technology offerings. We have an extensive IP library and full license access to JPL and Caltech's image sensor patents. Over the past 2 decades, we have developed a silicon-proven methodology, minimizing overall project costs and accelerated time to market for critical projects. Most importantly, Forza is committed to complete customer satisfaction in the long-term success. This slide illustrates the diverse range of markets and application areas where Forza has contributed through CMOS image sensor designs. We have worked all the way from automotive imaging to medical imaging to broadcast and digital cinematography, all the way to security and surveillance, high-speed data communication, and industry and machine vision. Forza has partnered with almost all the leading semiconductor foundries across the globe, catering to CMOS image sensors. Next, we will discuss CMOS image sensors for high-end cinematography applications. There are a unique set of challenges in designing CMOS image sensors for cinematography and other high-end prosumer applications. Particularly important are high resolution and high frame rates. Forza has extensive experience in designing CMOS image sensors for 4 different categories of high-end camera markets. First is the digital camera, where the target resolution is more than 4K and 60 to 120 FPS frame rate is standard. Second category is DSLR cameras. Third category is broadcast cameras, where the target resolution is much higher, typically more than 8K, and 60 to 120 frames per second is per second frame rate is pretty standard. One of the upcoming areas is virtual reality, where we have designed sensors up to 163 megapixels. Here are some of our primary R&D activities. We are doing advanced rolling shutter design. Stacked image sensor design is one of the hot topics these days. Here our target is to achieve the lowest dark current and low noise global shutter performance. Apart from this, we are actively working on reducing the read noise of sensors to be less than 1 electron and having very high frame rate at the same time, right? One of the most important focus areas is to achieve high dynamic range, particularly for automotive, medical, and prosumer applications. Next, let's look at the challenges in doing verification on CMOS image sensors. This slide illustrates a typical specification for a cinematography image sensor. We are looking at more than 100 megapixel full frame sensor with 60 to 120 frames per second frame rate. For the target application, we are using 65 nanometer backside illuminated CMOS image sensor process with 4 transistors and 2x1 diagonally shared pixel. The chip has a column parallel readout architecture with a 12-bit analog to digital converter. To generate high-speed clocks on chip, we have a phase lock loop which works with a 50 MHz reference clock, and furthermore we have multiple readout channels, each operating at more than 5 Gbps with serializers and 64-66-bit encoding on the chip. This is a typical block diagram for the cinematography image sensor as described on the previous slide. Majority of the chip area is occupied by the giant more than 100 megapixel pixel array sitting in the center in the full frame image sensor format. The pixel array is driven by the row logic block, which selects one row of the pixel array at a time and generates timing waveforms to stimulate the pixels for reset and TX modes. Since we have a column parallel architecture, the output of each column of the pixel array is buffered by a source forward stage called VLN, sampled and converted to a 12-bit digital signal by the single slope ADC. We have an on-chip ramp generator driving the ADC, an ADC counter which latches signal-dependent values in the analog SRAM on the chip. The digital logic samples the SRAM values for multiple columns and performs a 64-66 encoding before passing the data to the serializer. We provide a 50 MHz differential input clock to the chip, which is received by the clock receiver on chip, which generates a 50 MHz CMOS reference clock for the PLL. The output of the PLL is a greater than 2.5 GHz high-speed clock signal, which drives the serializer. This block diagram shows the analog readout chain or column circuitry, which consists of the pixel array, VLN, sample and hold, ADC, and SRAM. Now, in order to do verification of each of these sub-blocks, we have separate test injection points at the interface of each of these sub-blocks. This means that we can inject a known signal at these interfaces and verify the outputs of each sub-block separately. Now, this slide shows the block diagram of the digital output chain of our CMOS image sensor. The ADC output is saved in the analog SRAM as a 12-bit digital data in gray code format. The digital logic first converts the 12-bit gray coded data to 12-bit binary equivalent, and after that a packet of 64 bits is formed by concatenating 5 samples 12-bit binary data plus 4 bits left over from the 6th sample. In order to guarantee enough clock transition states on the CML driver, the 64-bit data packet is transformed into a 66-bit data packet via a 64-66 data encoding. Let's look at the verification challenges of the CMOS image sensor. A typical CMOS image sensor system will have a mix of analog and digital blocks. For highly sensitive analog blocks, such as comparators, you need to have an accurate and efficient methodology to simulate noise. Secondly, you need to verify CMOS image sensor large array-based architecture with column parallel ADCs and comparators with parasitics. So capacity of the simulation engine is very important. As you can see in the diagram here, there is a substantial content of digital blocks. So mixed signal validation of high precision analog blocks with digital control logic is important for functional verification of the CIS module. Next, let's look at the verification methodology and tool flow used at Forza Silicon to address these unique verification challenges for CMOS image sensor system on a chip. The verification of the CMOS image sensors can be broken down at 4 stages. First, at the pixel level, where we are interested in characterizing performance in terms of device noise, dynamic range, linearity, etc. The second stage of verification consists of the analog readout signal chain consisting of column circuitry. At this stage, we individually characterize the performance of each of the sub-blocks like VLN, sample and hold, ADC, and SRAM, both at the schematic level as well as post-layout extracted level. For the first 2 stages of verification, we extensively use Siemens analog fast spikes and Solido design environment to achieve the desired accuracy at significant speed up compared to our competitor simulator. The third stage involves doing static IR drop analysis of all the power and ground rails on the image sensor chip and dynamic IR drop analysis for the critical peripheral circuits. We have successfully adopted mPower for effectively doing EMIR analysis at Forza. Finally, in order to verify top chip functionality and pixel and ADC timings using row injection mode, we take advantage and the flexibility offered by Siemens Symphony mixed signal platform. First, we'll present a case study for analog block level verification with AFS Extreme Simulator. This is a brief summary about AFS. So as we all know, AFS continues industry leadership in circuit applications for EDA. So AFS XT solves IC verification challenges with precision, performance, and capacity. We can do all different types of analysis, including device noise characterization, parasitic simulations, device aging, mixed signal simulations. AFS is able to handle large test benches, large EM files, and can deliver performance at capacity. First, let's take a look at the analog block level verification using Siemens AFS Extreme Simulator. As a test case, we look at the RC extracted post-layout netlist of a phase lock loop or PLL with 2.4 GHz output frequency in a 65 nanometer CIS backside illuminated process. At the bottom, we can see that the total elements before reduction are over 100,000 RC dominated, making it a perfect example to validate AFS Extreme technology. First, we look at the output frequency and feedback frequency of the PLL after it has locked. We compare AFS Extreme Simulator with a competitor tool across different simulator modes, red, green, and blue modes for AFS Extreme, and CX, AX, and MX modes for our competitor tool. It is evident that the output frequency variation is higher for the competitor tool compared to AFS Extreme. Next, we look at one of the most important performance metric of a PLL, that is output jitter. Comparing the highest accuracy modes of AFS Extreme versus competitor, we can see that AFS Extreme red mode gives a more accurate peak-to-peak jitter performance versus competitor CX mode. Also, it is interesting to note that AFS Extreme blue mode gives comparable jitter performance as competitor AX mode as highlighted in the circle at the bottom. However, a natural question to ask is, how does AFS Extreme compare with competitor tool in terms of simulation runtime? The answer to that question is in this slide. AFS Extreme blue mode took 30 minutes versus competitor AX mode, which took 100 minutes. Therefore, at comparable jitter performance, AFS Extreme outperforms competitor tool by more than 3 times in terms of simulation runtime. Also, it is interesting to see that AFS Extreme also significantly outperforms the old AFS in terms of simulation runtime, which makes it evident that Siemens simulation tools are getting better and better over time. Even though we just showed PLL as an example here, based on our experience, AFS Extreme helps reduce simulation time a lot while keeping acceptable accuracy for blocks which need to be verified by RC extraction like PLL, high-speed counter distribution, serializer, and CML drivers. AFS Extreme benefits significantly when running RC extracted simulations. Next, we discuss how Siemens Solido design environment helped us to efficiently and accurately quantify the effect of process mismatch on circuit performance. Just a brief context on the Solido design environment, or SDE. It's a unified environment for all transistor level simulations and variation aware design verification across all statistical process corners. The AI powered engine speeds up any statistical variation with up to 1000x speed up compared to brute force accuracy. Solido design environment not only provides a design environment for performing transistor level parametric simulation, also there are powerful tools like PVT-MC verifier for doing up to 50x faster verification across corners for 3 sigma verification. Additionally, high sigma verifier tool can be leveraged for doing very high sigma verification for critical blocks where yield is extremely important. In the subsequent slides, I will cover one test case each with PVT-MC verifier and high sigma verifier for our block level circuit design in image sensors. First, we will start with PVT-MC verifier. This slide shows a 4 sigma Monte Carlo run for a clock distribution circuit for a 15 voltage corner transient simulation at typical corner. The PVT-MC verifier provides a probability density function shown on the top plot and a normal quantile plot shown at the bottom for each voltage corner. From the normal quantile plot, we were able to quickly identify a design bug where the duty cycle variation becomes severe for a supply voltage of less than 1.2 volts. Here, PVT-MC verifier provided a 4 sigma coverage with just 4,000 simulation runs, which is equivalent to running 10 million brute force simulations, thus saving precious engineering resources needed for debugging this issue. Next, we will show a test case where Solido high sigma verifier helped us in ensuring high yield with a CIS chip containing 500,000 ADCs. As shown in the slide, we used Solido high sigma verifier to estimate a 6 sigma spread of a sense amplifier offset voltage. With just 9,000 simulation runs, we were able to accurately predict a 90 millivolts 6 sigma offset voltage, which would be equivalent to running 10 billion brute force simulations. Another extremely useful feature of the Solido high sigma verifier is that it generates a verification plot confirming that the same level of accuracy was achieved as brute force Monte Carlo run. This is as shown in the graph here. Finally, this slide shows my personal favorite feature which I regularly use as a designer. Solido also provides a quantitative sensitivity analysis showing the impact of various circuit device parameters on the output metric. This further helps you as a designer to optimize circuit device sizings to minimize the spread of your output metric. Now we'll switch gears and I will discuss Siemens M-Power enabled full chip static IR drop analysis on a huge CMOS image sensor chip that is currently in use by our customers in their cameras. Forza has designed some of the largest CMOS image sensors in the world, stretching design flows to the limit. This chip shown on the slide is one such example of an ultra large format image sensor that we have designed. It contains about 2.5 billion transistors and is 10 centimeters tall and 8.5 centimeters wide. This was fabricated using a procedure known as 2D stitching and contains about 500,000 ADCs on the chip with a total power consumption of about 20 watts. Any EMIR tool will be pushed to its limits while even doing a static IR drop analysis on a sensor of this size within reasonable machine runtime and memory usage. I will show in the subsequent slides how M-Power enabled us to complete an IR drop analysis on this sensor with very reasonable machine runtimes and RAM usage. So what is the challenge in doing static IR drop analysis on this sensor? Well, as you can see, there are a total of 2.4 billion transistors on the sensor. The large format sensor array itself contains 1.6 billion transistors and 800 million transistors in the peripheral circuits like the row logic, ADCs, and SerDes blocks. On top of the large number of transistors, the sheer physical size of the sensor is huge, with the width being 8.5 centimeters and height 10 centimeters. This presents a high capacity IR drop analysis challenge for any EMIR simulator. There are multiple power rails on the sensor, but we will focus on the most challenging power rail called VSF PIX here, which brings power to the pixel devices from the sides. For the first silicon success, it was critical for us that the IR drop solver we adopt is capable of analyzing this critical net. This slide further illustrates the VSF PIX static IR drop analysis challenge. The VSF PIX pads are located on the left and the right side of the pixel array with an overall separation of more than 4 centimeters from the pad to the center of the pixel array on each side. The VSF PIX is routed from the pads to the pixel array and is grid interconnected over the full pixel array. In this image sensor design, we read 6 rows of the pixel array at a time, totaling about 110,000 pixels. Due to the column parallel nature of the readout, each pixel output source follower in the column is biased with about 18 microamps of current pulled directly from the VSF PIX supply. With this context, the main challenge is that any IR drop solution must be capable of analyzing a significant portion of the whole pixel array without compromising on accuracy. Setting current sinks on the 110,000 pixels in an easily programmable fashion is also very important. Here is the setup flow for our legacy EMIR tool. First, we take a LVS clean layout and strip out any front-end devices such that only the routing layers and vias are present. Second, we manually put current sources and sinks labeled in the layout. Third, we use a home script and ad hoc text file to run the legacy tool on this manually post-process layout. And finally, the output from the tool is a thermal map with static IR drop information. So what were the issues with our legacy flow? The most critical problem is the additional manual data preparation step needed to post-process the original layout. Not only does this waste precious engineering time, it also has a huge risk of unintentionally introducing layout errors. Another major problem is that there is no flow integration. Homegrown scripts may lead to errors, especially for newer process nodes, thus requiring dedicated flow experts. Our legacy flow performance also degrades significantly at scale, leading to long run times and high peak RAM usage, necessitating servers with enormous amount of RAM. Additionally, there are secondary problems like the need for manual current assignment, which not only increases setup time, but could also lead to unintentional errors. Currently, our legacy solution can only do static IR drop analysis, and therefore a lot of peripheral blocks in the image sensor architecture which have switching currents cannot be analyzed accurately. To solve all these challenges we are facing, that is where Siemens Empower came to our rescue. Empower provides a Calibre SVDB and AFS compatible platform for doing static and dynamic IR drop analysis at full chip capacity and performance. There are capabilities in the tools for automatic current assignment. In the subsequent slides, I will show the VSF PIX static IR drop analysis results with Empower and the comparison with our legacy solution. So here is the setup flow with Siemens Empower. The first step is the FSDB database from the Calibre LVS clean layout can be directly imported into Empower without any manual post-processing. Then any EMIR standard files like ITF, PTF, or XACT, which are usually provided by the foundry, can be directly used for analysis. Third, the region-based or spatial current assignments can be done with providing coordinates in the script. The mPower Output Visualizer GUI displays the thermal map of the static IR drop, providing additional insights like the worst case resistance path, etc. So clearly, the caliber integration makes the tool easy to use, and a standardized text file format minimizes chances of manual error. This slide illustrates the VSF-PICS static IR drop analysis approach. The VSF-PICS grid symmetry dictates that it is sufficient to analyze 1/4 of the pixel array, which is effectively 4,000 pixel rows containing 400 million total devices and 800 million devices on the VSF-PICS alone. As mentioned previously, only 110,000 devices are active at once. Successful analysis of this subarray is essential for Forza's IR drop solution. Okay, so the main question remaining is, how does mPower performance compare quantitatively with the legacy EMIR flow at Forza? As shown in the comparison table, for the same accuracy, mPower runtime was 3 times faster with 35% less RAM usage compared to the legacy EMIR flow. Previously, what we could simulate on a 1 terabyte RAM server, now we can simulate on a more modest 500 GB server. Additionally, mPower gave much more deep insight into the aspects of layout limiting the static IR drop. So, for example, mPower can provide information like limiting resistive path, which is extremely useful to further optimize the layout to improve the IR drop performance. With our legacy solution, any layout improvement for reducing IR drop would be very tedious and an iterative process involving senior engineering staff. This empowers resistive path tracing, saves valuable engineering time. Further, as shown in the image, mPower's extensive results map, whether reviewed individually or with synchronized browsing, allows Forza engineers to verify design intent, scenario definition, and removes guesswork from interpretation. In terms of our mPower adoption roadmap, till date, we successfully adopted mPower in our static IR drop flow. The next step for us is to go one step further to take advantage of the AFS integration of mPower to perform dynamic IR drop analysis on the peripheral circuits. This is something which we cannot do with our legacy flow, and we are very excited about it. This is the expected dynamic EMIR flow with mPower. The only additional step compared to the static IR drop analysis is that the FSDB database from AFS run can be imported into mPower to take time-dependent current profile for each transistor. So, to summarize, due to multiple benefits like caliber and AFS integration, flexible current assignment, and performance at high capacity, mPower has been successful in removing EMIR-related risks from our image sensor designs, thus improving yield and growing confidence for first silicon success. Next, we switch gears and look at the mixed signal test case for our complete top chip schematic for our cinematography image sensor. Our goal here is to do a full chip functional verification, and we use Siemens Symphony mixed signal simulator to achieve our verification objective. Symphony is a flexible mixed signal simulation platform which offers AFS and AFS Extreme as the analog solver and allows any digital simulator of your choice, including third-party simulator for simulation. This is a row injection test bench for doing full chip functional verification of our image sensor. We have all the analog blocks with the spectre view and the digital blocks are using RTL, either Verilog or Systems Verilog. As you can see at the bottom of the slide, we have more than 600,000 total elements in this Symphony netlist. This slide shows the tool setup for Symphony, which essentially combines AFS as an analog simulator and the digital simulator of your choice into one platform. For the digital blocks, any valid view like functional or external HDL is supported as shown under design configuration. For the interface between digital and analog blocks, we can define boundary elements with variables like I/O voltages, rise time, fall time, etc. as shown at the bottom. Now let's take a look at the Symphony results for our full chip functional verification for our CMOS image sensor chip. On top, we see a ramp signal, pixel output line signal, and other sensitive analog nodes in the readout. We also see some important ADC timing signals which are in the digital domain. Below that, we can see important pixel timing signals like the reset and TX. Finally, at the bottom, we can see the gray-coded ADC counter and the output ADC latch with time of arrival proportional to the pixel signal level. The output of the ADC is latched onto the analog SRAM on chip. Next, we look at the results of the 64-66-bit data encoding and serial data communication. As shown in the figure below, the 48-bit gray-coded output of the SRAM for a particular row time is first converted to its binary equivalent, and then the digital logic combines data from multiple row times in a 64-66-bit encoded data stream. The encoded data is serialized at more than 5 Gbps data rate and transmitted out using a CML driver to be decoded by an off-chip FPGA receiver. In this test case, the first packet from row 1 and row 2 are 0A5 and 992 respectively, and the image snippet on the top right shows the decoded data pattern at the FPGA receiver. It is clear that the decoded pattern exactly matches what was transmitted, hence validating our full chip operation. Finally, to conclude, CMOS image sensor for cinematography have very high resolution and high frame rate requirements, posing stringent verification challenges due to column parallel architecture and high accuracy requirements. We presented multiple case studies demonstrating effective integration of various Siemens tools in the Forza design flow in the context of CMOS image sensor design. First, on the analog side, we showed that AFS Extreme provided a 3x performance improvement over the competitor simulator without compromising on accuracy. On the design variability side, we showcased how PBTMC verifier and high sigma verifier under Solido design environment provided tremendous simulation speedup compared to brute force approach. This helped in yield optimization and saving precious engineering time. On the EMIR front, we presented that mPower provided an automated workflow with a 3x runtime improvement and 35% memory reduction compared to manual legacy solution. Finally, Symphony provided an easy to adopt, flexible and robust platform for doing top chip mixed signal verification. That's the end of my talk, and thank you all for your time.